Hi, everyone. As Joanna said, my name is Lee Hannigan. I'm a Senior Specialist Solutions Architect for DynamoDB. Been with AWS almost 7 years now, I think. Or is it almost 6? I don't know. I lost count. But yeah, it's been exciting. I typically work in the NoSQL domain, but I have some sort of background in big data and analytics as well. Today, we're going to talk about scaling with DynamoDB. And if you think of scaling with DynamoDB, the first thing you have to think about is a data model. If you design a bad data model in DynamoDB, you won't scale like you would expect. We're going to do that with a case study with Genesys. So Claire, who's a software developer manager with Genesys, is going to take us through a specific use case on one of their use cases for DynamoDB. So a talk like this, I find them tricky sometimes. Especially you have people who've used DynamoDB. Hands up if you're familiar and use DynamoDB. Okay, then we can power on a little bit. But it's important that you don't leave some of the audience behind. Some people might not have the same level as other people in the room. And I am going to attempt to set the stage for Claire, so when she goes into a little bit more technical details about what they've done, that the room will be able to understand. So I'm going to start with an analogy. And a perfect analogy is a phone book. Who's familiar with phone books? Who remembers phone books? All right, all right. For those of you who don't know what a phone book is where we used to have to find a person's phone number back in the day. Not as efficient as it is now, but there we were. So if we think about a phone book, there's a delay in those slides. If we think about the phone book, typically your phone book was, I don't know, per county, for example. I would pick up one for Kilkenny, and I'd be able to say, you know, for this person, Lee Hannigan in Kilkenny, what's his phone number? And that's a really, really fast search. If you think it's basically a binary search, super fast, super efficient, you just point straight to where you go, middle of the book, Hannigan, and you're looking for Lee. So DynamoDB is built basically like that. If you have a mental model of a phone book in your head, then that's basically how you fetch data or retrieve data in DynamoDB. So if you remember a phone book, it was broken up into two sections. You had the normal phone book at the front, but at the back you would have the yellow pages, and then I think maybe years later they divided them into two books. But for this use case, it's the same book. Yellow pages at the back, normal people at the front. So like I said, it's binary search. I can do things really efficient where I can say, all right, for Kilkenny, I want to find Lee Hannigan. So Kilkenny, in DynamoDB terms, would be our partition key. That's the book that we're talking to, and that defines the partition key. So you know straight away that you can go and get the book for Kilkenny off the shelf really, really quickly. And then we need to sort the data. And we can sort the data anyway, but if we're relating it to a phone book, then typically it was sorted by surname first, and then first name. So that allows you to really efficiently say, for Kilkenny, find me Hannigan Lee, find me Purcell Claire, and that was super efficient. I can do things like, in Kilkenny, give me all of the people whose name starts with H, whose name starts with HA, and that would list all of those people. But what can't I do? Can I search for all of the Lees in Kilkenny? No. Think of a phone book. If you wanted to find all of the Lees for Kilkenny in a phone book, you're going to have to read that entire book and take out all of the Lees because it's ordered for last name first. So Lees are scattered everywhere throughout the book. And that's exactly the way that DynamoDB is built. So then if I go back and think about the yellow pages at the back, in DynamoDB, the yellow pages at the back of the book, we would call a local secondary index. It's local because it's in the same book. And you get benefits from having things in the same book. You get strongly consistent reads. So when you write to data in a DynamoDB table, it propagates to the index immediately, just like the phone book would. So the partition key remains the same because it needs to remain in the same book. The book is named Kilkenny in this case. But we get to order it different at the back. So yellow pages were for serving businesses, so you want to look up a bar or a restaurant. I'll definitely be looking up a bar later on. But yeah, you know, if you wanted anything in business, you wanted a handyman or whatever it was, the yellow pages was where you done it, and in DynamoDB, that would be a local secondary index. Then we have what is known as a global secondary index. A global secondary index unlike the Kilkenny book, we defined a new book, which would have been located over on the other side of the library. So it gets us, we have a unique book now that's specific to doing one thing, and in this case, we're looking up error codes. So for a specific error code, I know it doesn't relate to Ireland quite well because an error code is a specific building now, but think of the UK where they have their postcodes. You can go to a specific postcode and you can find all of the users or all of the people in that postcode. Similarly, I could have changed this where I could have used the partition key as phone number, for example. And then you get a reverse lookup for this phone number. Who is the user? Super quick, super fast. It's basically binary search once again. So that's a global secondary index. It gives you a flexible view of your data. Maybe your base table is really good at one thing, but this flexibility where you need the error code or the phone number, that's where a global secondary index comes in. So it just gives you a little bit of flexible processing. Then we need to talk about updates. So updates to your phone book. In DynamoDB, you never update an index directly. The updates always go to the table or the main book. So your updates go to the book. We know that in the same book, we have our local secondary index, which is your yellow pages. So that's applied immediately. But the other book for the error code is over on the other side of the building. So what we do is we employ these really fast librarians who capture the write, leg it over to the other side of the building, and apply the write to the local, or the global secondary index. So there's an eventually consistent problem there. There's an extra hop. So global secondary indexes can only give you eventually consistent reads. It's more flexible than a local secondary index, which can give you consistent reads. So we're talking about books and things, but there also has to be a physicality to this. Where are we going to store these books? And typically, we store books in a library. But what happens if there's a fire or there's, some construction on the road that's outside the library? Then you can't get access to your book. If there's a fire, your book's gone. You're never getting it back. If there's construction, the access is slowed down, or maybe you don't get access at all. So we need to think of a way to store our books that's better than putting all our books in a single library. So we decided we'll keep 3 copies of each book. And let's call 3 copies in different libraries, which we'll call availability zones. So there's always at least 3 copies of your data. So now what happens if there's a fire in one? You can access the data in the other 2. But then we need to think about rights to each book. We need to update a book. We could, I suppose, elect a leader, a library leader. So all of the rights go to the leader library and then synchronously replicate out to the other 2 libraries. But if there's a fire in that library, all of your rights and all of your strongly consistent reads are done. You won't be able to serve them. So what we actually do is we have every book elect its own leader in any one of the 3 libraries. So rights to some books are in one library and other books are in the other. So if there was a fire in one library, then the other books would work. And the library that's on fire, those leaders will be pushed over to the other libraries really, really quickly. So it really eliminates any downtime. So now we have to think about accessing the books. So books in a library goes on a shelf. So now a shelf is a partition in DynamoDB, a physical partition. So you take your books and you put them on shelves. So like I said, we have 2 wings. We have the error code wing over here, and we have just the normal county wing for Kilkenny over there. So you have your main table and your global secondary index. But then we need to think about placing the books. So you have books, there's counties. Alphabetically would be your first attempt or your first try. Logically, it would be almost right. But most people in Ireland at least live in Dublin. So we have this large book on the Dublin shelf, but then we have Donegal, Derry, and Down, I think. Is that it anymore? No, I think I have them. So you've got a lot of books on the same shelf. And as the Dublin one keeps growing and growing and growing, eventually something's going to happen to the other books on that shelf. So a better way to do that is to create a hash of the book. So you supply the book as is, and this really fast librarian hashes that book and decides what shelf to put it on. So now we have much even distribution of our books. So Dublin, Derry, and Donegal are no longer on the same shelf. They still share the same partition key, but behind the scenes, that librarian has sorted it out in a hashed format. Now, with each one of these shelves, they have a physical nature, so they have a size limit. So what is the size limit of a shelf, and what happens if you exceed that size limit? So if you exceed the size of a shelf, so let's imagine Dublin is co-located with maybe Cork or Galway, which are other large counties and cities. We need to split it, and we need a way of splitting it, and the easiest way to split it is just split it in half. So we take a single shelf, and we make two out of it. Half of the records or half of the books go to one shelf, and half of the books go to the other shelf. But what if a county or area code gets bigger than the shelf itself? So we have a county like Dublin, or that's probably related maybe to New York or something that's much bigger, and that book has just got so much bigger than a shelf. Then we split it down into subcategories based on the sort key. So we can actually take the New York book and do it by postcode over there. So you have New York from A to Z, or A to C, and New York from D to whatever, and we split it based on sort key. So we can't have a maximum size limit of how much users we put into the New York City book. We can just keep splitting shelves and distributing the books. Now, access limits is a different thing. So you have books on a shelf, and your users want to access those books. But those books have a limited amount of, let's call it throughput, I suppose. So what do we do when there's so many people queuing to get to the Dublin book, which is the busiest book? We simply split those in half. So one book, or one shelf now becomes two, and we can actually isolate a single book to a single shelf. If I put that into DynamoDB terms, we can isolate the item on its own. So we can take a large group of items, and we can isolate it down so much that one single item sits on one shelf or one partition on its own, which will give you the full capacity of that partition. Joe talked about this earlier if you were at that talk, but each partition can give you 1,000 write capacity units and 3,000 read capacity units. So quick review before I pass it over to Claire. Library shelves are DynamoDB partitions, so you have shelves, and you put books in those partitions, which is your items, partitioned by whatever county or whatever your partition key is. It's always replicated across 3 availability zones, always. DynamoDB does not allow you to specify a replication factor. Your data is always durably stored and highly available. Each table has a partition key. The sort key is optional. A partition key on its own is known as a primary key. A partition key that has a sort key, both together are the primary key. A primary key in DynamoDB must be unique. You can use LSIs and GSIs, so local secondary index and global secondary index, to give you different access patterns or to serve access patterns that you may not have known in the beginning of your application but have arisen over time. And writes always go to the base table, propagate to local secondary indexes instantly, and you have that fast librarian for the global secondary indexes. Tables start based on your needs, so the amount of shelves to store your books. If we're thinking of an on-demand DynamoDB table, when you create one, I don't even know where this number came from, but we came up with the idea that 4 partitions would be enough. So a new on-demand table can serve 4,000 write request units and 12,000 strongly consistent read request units out of the box. Again, if you're listening to Joe's talk, we have this new feature called warm throughput. If 4,000 isn't enough for you, you can just tell, hey, DynamoDB, I need 100,000, and it will scale up for you. The beauty with DynamoDB is when it scales up, it never scales back down. You don't pay for the scale up here, you pay for what you use. So that's a really nice. And even though you start with just 4 partitions, it can naturally increase. So on-demand tables have about a 50% tolerance. So once you go above 2,000 writes for an extended period of time, it will actually split to the capability of 8,000 writes and then split again to 16,000 writes and so on. So the partition key is the most important part of your DynamoDB data model. It will specify which partition your data goes to, but it will also, it's what you need to know at runtime when you need to fetch that data. So with that, I'll hand you over to Claire, who is going to take you through how Genesys built applications on DynamoDB and some of her learnings, which are quite interesting. Thanks, Claire.
Thanks. Hello, everyone. I'm Claire Purcell. I'm a software development manager here from Genesys to talk to you about how we modeled our data in DynamoDB in our team. So first, a quick bit about who we are. Thanks to Joanna for the great introduction, by the way. Genesys are a global cloud leader in customer care. We have 6,000 businesses, or over 6,000 businesses, running their contact center on Genesys software. And we have over 1.5 billion conversations served per month. We're globally available, as you can see on the map. So we serve organizations in over 100 countries. And we do this via 20 distributed regions, which are strategically located around the world. So Genesys Cloud runs on close to 500 microservices, each which have their own data modeling needs. We work closely with our architecture team in order to find and use the right tools for each job. So where it's overwhelmingly DynamoDB in Genesys, this is the right tool for most jobs we have found. There are also other teams who are using other AWS services such as Aurora and RDS to suit their data modeling needs. And indeed, I am talking about one way in which our team used DynamoDB, but there are teams which use DynamoDB in different ways throughout our platform also. So starting with the use case, to put some context on what our services actually do, this is what it might look like when an agent is communicating with an end user in the contact center. So our service stores all of the interaction history for that end user in the blue box over there on the right-hand side, and then serves it up to serve a UI for the agent when they're interacting with that end user. So this gives them a comprehensive history of all of that user's interactions, and this helps give the agent a more rounded view of the journey so far with the organization. Before we discuss the use case a bit further, I just want to explain some definitions, not to make any assumptions of what people might be thinking the same way as me. So first of all, a session is the representation of a Genesys Cloud conversation, a web visit, or a mobile app session in our service. A communication refers to a subsection of a conversation. So this contains details relating to a customer or an end user, an agent, a routing flow, or a queue. A contact is the representation of the end user in Genesys Cloud. So this would be the customer who is interacting with the contact center of our customer. Giving context to those definitions, the contact is displayed on the top and left of the gadget here. You can see the Cara Reynolds name. The sessions are in the list view over on the right-hand side, and the communications, while they're not surfaced in the UI right now, you could imagine it would be like an expansion of one of those sessions. So what we were doing before this particular project was we were still using DynamoDB, but in maybe a little more traditional way. Consuming one event meant we were updating one record in the table in a straight upsert. But we needed to extend that data model in order to be able to enable several new features in Genesys Cloud. We needed to extend it to include these communications for a conversation, so the extra information. In doing this, we needed to maintain backwards compatibility, so we needed to allow services to retrieve all sessions for a given contact. And we wanted to provide flexible query patterns to allow our clients to retrieve and filter the data that they require in order to suit future use cases. We also, most importantly, wanted to store these items in a cost-efficient manner to suit the high throughput of conversation events in our platform. So if we were to just stick these attributes into lists on the existing data model, what's the worst that can happen? Well, right now, we had 4 different lists. So we had the customer communications, flow communications, queue communications, and the user communications. But for future use cases, such as supporting bot sessions, that's another extra list. Outbound campaigns, another extra list. As you can see, over time, as we're adding more and more lists onto this one object, we're getting an overbloated model, essentially. Most importantly, each time we would be writing to this record would mean that we'd be updating the entire record. So we might consume an event that only wants to update one customer communication in that list. Well, we're still writing back all of those flow communications, the ACDQ communications, Basically, we're paying to upsert the entire record just to update a small part of it. So a bit about how this might look. I'll talk you through the life cycle of what a conversation session record would have looked like had we done this. So first of all, we have a customer who would join the conversation. In order to write that session when it was created, with some base level fields and then also with the customer communication, it would cost us 2 write capacity units. So this is because we're writing to the main table and then it's being projected to the GSI, as Lee explained earlier. Next, the conversation is routed. So this means that a routing flow communication is added. Well, this bumps up the size of the record to over 1 kilobyte. So then it will cost us 4 write capacity units to write for that event. When the conversation moves to a queue, we're adding another communication. It still stays around the 4 write capacity unit mark. But then when an agent picks up the conversation, we add a user communication and it bumps it up to 6 write capacity units. So obviously this unbounded growth isn't ideal, but it's made much more apparent for asynchronous conversation channels. So something like email. Each one of those phases that I described in the previous slide corresponds to 1 email being sent in one direction. So it's costing us, I think, a total of 16 write capacity units just to process 1 email. If we want to write an event for an email thread which has 3 emails on it, that's costing us 10 write capacity units for 1 event. With 5 emails on the thread, 16 write capacity units. So it just does keep going up and up for channels that have multiple phases. And this isn't just for emails. It can be a call that has been transferred between different agents and queues as well. So in order to limit this growth over time, what we did was we looked into a way to be able to write records individually, splitting them out. So the solution to our problem was single table design, which allowed us to store this relational data in a NoSQL database. We chose it because the session and all its associated communications could be read together in one request from the table. And also it allowed us to store things separately so items could be written individually, which meant we weren't updating all the communications just to update one of them. Another team had already implemented this pattern as well, so we were able to get lots of information from them and some lessons learned. And with vertical partitioning, we were able to reduce the overall write cost by writing single items at a time. Implementing this looked like adding partitioning. So we glued the objects together by partition key. They would have a shared partition key, which was the organization ID and session ID. And then we differentiate them by having a different sort key. So in this case, the communications all had a certainly prefixed sort key, and the base session item had a hard-coded string. So if we wanted to query for a session and all of the associated communication records, we just query by partition key. That gives us the full history. If we want to get a specific communication, we just add the partition key and also that sort key. Same for the base session. And finally, if we want to do some smarter filtering, similar to what Lee discussed earlier, we could do a start with com. So we have all of our subrecords prefixed with the same string. So this would allow us to retrieve all of the subsections of the conversation. In terms of how we've structured our global secondary index, there's one on the table used to retrieve all sessions for a given contact. We have structured it in such a way on this table that we write only the parent record to the GSI, and also we use include projection type to only project the fields that are necessary for filtering. This is because we can filter the sessions out on a smaller version of the data with only the important fields, because filter expressions are applied after the read is actually executed. And that means that we're essentially spending less to read from that index, right? So in order to query all the sessions from an index, we first have to query the GSI, the filter expression is applied, and then we will read back all of the filtered partition keys from the main table. So now the new life cycle of a conversation record looks a lot nicer. It's bounded at 3 write capacity units per event. So this is made up of writing to the main table, writing the communication record, and also then the projection to the GSI of the base communication, or the base session item. So what we would have seen in the blue line there, where the size was going up and up over time, instead now it's bounded, and that's bounded across the conversation phases as well. So for our email thread with 5 emails, it's still only costing us 3 write capacity units per event consumed. In terms of the trade-offs to the approach, you might be thinking, but now you need to read a whole lot of items altogether. What's going on with the read capacity units, and also with the way that the GSI is put together? Well, reads make up 0.01% of our throughput in this particular service, so it was very much worth it for us to be able to bound the writes and to put the emphasis on keeping that write cost down and keeping the size of that down. Still, in the way that the GSI is structured, we are making a best effort with the limited projection to the GSI to make the smaller size. And over time, this all just, it works for this service because of the nature of the throughput. So, in conclusion, there isn't a one-size-fits-all approach to data modeling. You got to think about your throughput and access patterns. Those are essential to figuring out what the best data model for your service will be. It's worth thinking about what data really needs to be projected to the GSI in order to fulfill your access patterns. So limiting the data in the GSI could work out cheaper for writes, like it has for us, but it could be more expensive for reads. And single table design we found to be a good approach for modeling relational data in an NoSQL database. Thank you very much, and please fill in the survey.